let us talk about outliers. So what is an outlier? An outlier is a example or an observation that is very different from others, and sometimes they're called anomalies. Um, yeah, I'm actually not going to go look at these CPSC 340 slides right now, but you're welcome to look at them. And the point of them is it's kind of hard to, outlier is a very not clearly defined. What does very different mean? If you have a house that has 100 bedrooms, is that an outlier? Yeah, probably. If you have a person whose income is $1 billion a year, is that an outlier? Yeah, probably. And so when you just look at one feature, you might really see outliers, but sometimes it's more complicated and you need to look at multiple features. Like you might have a house that has 6 bedrooms and 1 bathroom, and having 6 bedrooms isn't that crazy. I mean, it's pretty unusual. Having 1 bathroom isn't that crazy, but the combination of them is very bizarre because how are all those people going to do their business in a timely manner? It would be relatively unusual in a data set of houses. And so sometimes you can't just look one feature at a time, and the outliers actually depend on all the features. And so it's a very nebulous field, but it is important because if you have outliers that are in there because of data quality issues, like they can potentially really mess up the work we do here. And so I'll be showing you that later today. Why do we care about outliers? Yeah, one of them is, as I just said, they shouldn't be there. Someone typed something in wrong into the data set, and now it's just going to mess everything up. Another reason is actually not because we want to find the outliers to throw them away, but because the entire task we're doing is just to find the outliers. For example, credit card fraud detection. So we actually had a credit card fraud detection data set earlier on in the course. If you recall, that was when we were talking about precision and recall and all of that stuff, and we wanted to get high recall on the frauds. But that was a supervised outlier detection in the sense that we had the label in our training set. Was this a fraud or not? So put another way, was this the type of anomaly that we're looking for or not? And so in that case, you could kind of just treat it as a regular supervised learning problem because you have the labels, and you might not need to put on your outlier detection lens as much. But what we're going to talk about today is that no one's given me a labeled data set saying this is an outlier, this is an outlier, this is not. And so we just have to figure it out on our own. And so we'll talk a little bit about how to figure it out on our own, and a little bit about how to defend against outliers, and a little bit about the implications of outliers. So how can we find outliers? Yeah, we can look at a bunch of plots. We'll look at a scikit-learn function that tries to find outliers for us. And we'll look at some ways of leaving outliers in and not worrying so much about it. Okay, yeah, this will make more sense later. Questions about this overview? Is there any metric to ensure us whether the value is an outlier? Yeah, that's the thing. I mean, the problem is that there are many, many definitions of an outlier. And so talk about some of those in 340, and you can look at those slides. But I think the problem is it's domain specific. You can try to come up with general ideas, but it is hard to do that entirely. And there's many ways you could define an outlier. So yes, there are ways, but overall, it's a very nebulous endeavor. Okay, so what we're going to do next is what I'm calling the outlier scavenger hunt. And so what I'm going to do is just pull up some data sets we've looked at earlier in the course and just see if we find outliers. So if you recall the census data set, this is now a while ago, lecture 6 and 7, we were trying to predict the target variable was the higher income level or the lower income level. And we had all these pieces of information that people filled out on the census. So we had 26,000 census people in our training set. And we mentioned back earlier in the course this pandas profiler thing. And that's kind of a nice way to, at a glance, like see what's going on in your data set. Because, for example, it gives you all these histograms for all these variables, age, work class, education, marital status. So at the very least, you can look at features one at a time. And so here, for example, with capital gain, the fact that it's showing me, what is that, 100,000? There's a very faint blue bar here. It looks like there's someone whose capital gains was way bigger than everyone else's. And so that person might be an outlier. Likewise with capital loss. And so this is kind of nice, although it's only looking at features one at a time. Pandas profiling actually has a way to look at features more than one at a time. Did I? Scrolling is so bad. I think it's because I did minimal equal true. Let me run this while I answer your question. And I know it takes longer when I don't. Oh, that didn't take longer. Oh, weird. Anyways, I thought it was showing me, would show me some other things, but it isn't. So let's just move on. Next question in the chat. Would a lack of training data for a specific feature be a reason to consider points as outliers? Okay, so for the most part, I'm only going to talk about numeric variables as outliers. You could have a category, like what the thing was in the midterm is there was a categorical or an ordered integer feature, an ordered discrete feature, and you had very little of one category. But I mean, you could in that case because it was ordered, I guess. But it's yes. I mean, having something be rare is part of the definition for it being an outlier. Like the fact that it's huge isn't enough because maybe all of them are huge and one of them is really small and therefore it's an outlier. So yes, rareness or unusualness is a measure for outliers. And you could have a categorical variable with very few people in a particular category, but you wouldn't often refer to that as an outlier. It's usually about numeric variables and thinking about the magnitude. And I think I can explain why more clearly later today with some of the stuff we're going to talk about. Okay, where's my, yeah, so here's this capital gain thing again. I'm making a histogram of that. And so we can again see that most of the people have capital gain close to 0, but some people have this very big capital gain. And so here's all the ones that are strictly greater than 0. And we can see there's still a bunch that are small and this few number of people who have this much bigger capital gain. So maybe those people could be outliers. The question to ask yourself here, and this is kind of similar to the class weight discussion we had. Do I care about precision? Do I care about F1 score? Should I change my threshold? It's a very domain specific question that you need to ask yourself. Okay, I have this. This is weird, but is it actually a problem? Because if everything's fine, it's not a data quality issue, then we might not really want to do anything about this because that's what the data it says, and we're just going to leave it alone. But if you suspect that there's something fishy about this, you might want to consider removing it. And we'll keep talking about that as we go through the day. Okay, so isolation forests. So I'm not super familiar with these, but I heard about them, and so I went and looked them up. And they're implemented in scikit-learn. And so they're basically like an outlier detection method built into scikit-learn. So someone asked earlier, like, is there a way to find outliers? So there's not the only way, but this is a way. It's a scikit-learn thing. And it's kind of like decision tree or random forest, but it makes random splits. And then if a training example gets by itself quickly, then it's considered weird. Because if you have a whole cluster of points that are very similar, you're going to have to keep splitting and splitting to get each one by itself. But if you have something by itself, you just make a few big cuts and you'll isolate it. So that's why they're called isolation forests. So I'm going to take the housing data, and this is now a scikit-learn function, so I have to do the pre-processing again in order to actually pass it in. Oh, sorry, not the housing data. This is the census data. So here's the syntax. I make an isolation forest. You can call .fit. You can call .predict. There's a fit underscore predict, just like fit underscore transform does fit and transform together. Fit underscore predict is shorthand for doing fit and predict together. And well, first let me show you what it outputs. I see the fitting is taking a bit of time. So it outputs zeros, plus ones and minus ones. So it outputs +1 for an inlier, meaning not an outlier, and -1 for an outlier. And so if I do this, if I get all the cases where it's negative, that's going to grab the outliers for me. And what it does is it grabs 193 cases that it decided were outliers. So according to this scikit-learn isolation forest, the details of which we're not going into here, out of the 20,000 people, it considered 193 of them to be somehow strange. So that's pretty useful. That's funny. When I ran it myself, I got 61, and it's almost certainly because of the random state thing. Now I got 100, and hopefully when I run it again, I'll get 100 again. Great. Okay. Also, 100 is kind of a weird number. I don't want it to confuse people and have them think it's exactly 100. Bam. Okay. I see a question in the chat. Yeah. So why does random state make a difference? Like random forests, isolation forests have some randomness in them, and so it had said in the text that it found 60 something outliers, but it said in the code it found 100 something outliers. I just wanted to fix the random state so that every time you run the code, it gets the exact same answer, so that I could put it into the text and have the text match what the code was outputting. That's all. And it's just nice when you're following along. If you're running the code, you get the same results as I get. So it's kind of nice, especially for teaching. To get to the earlier question, so let me click on this documentation. There's so there's this picture in the scikit-learn documentation. There's only 2 features here, so it's not really that realistic of a scenario. But basically, you can imagine that if you're just randomly splitting here, like a decision tree, so if you're just randomly splitting all over the place, then what's going to happen here is that here, with this many random splits that I did, this point here is already by itself in a region, and this point is by itself, and this point is by itself, and this point is by itself, this point is by itself. And so if you just randomly split things, the things that get to be by themselves in a region faster are more weird because there's nothing near them. Whereas all of this stuff over here, it's going to take a lot of splits to get any of those points to be all by themselves because they're so close to each other. And so the longer it takes for a point to be by itself, the more outlier-y it's considered. Great. Okay. Let me go back here. Oop, that is not good. How do we distinguish between another outlier and a cluster? What do you mean by that? Could you elaborate on the question? Like if there are 3 points close to each other, are they a cluster or just outliers? Yeah, so that is indeed, and in those 340 slides I linked to, it talks about that as well. Like that is genuinely an ambiguity in the definition of what do you call an outlier. Does it have to be literally by itself? If there's just 2 points right next to each other, then you call those are probably still outliers too. So yeah, it is a tricky business to say what an outlier is. And I think what this might be doing, oh gosh. I think what this might be doing is it might be doing like multiple rounds of these or something. When we have so many features in census is the way of finding out why the isolation forest thinks these are outliers. I don't actually know. So we're getting to the limits of my knowledge about these isolation forests. But hey, what would I do if I really wanted to know this? I can demonstrate it for you. I would go and look at what the attributes are. Okay, it has a bunch of estimators, which are these random tree thingies. That's very interesting. Okay, I'll have to look into this more, but this causes me to raise my eyebrows. I wonder if it's subsampling the data, and maybe that would take those 2 points next to each other into account, because in one random sample of the data, only one of them is there, and so then it still gets considered an outlier, but I have to look into this more. Anyways, to go back to the question of which features, subset of drawn features. Yeah, my guess is just looking at this documentation that it probably doesn't have an easy way to tell you which features are important, because it tells you something about features, but I think those are just randomly picked. So I don't think there's anything to it really. That's my guess. If I wanted to know that, this is where I would have gone to look first, and this would have been my first impression without further investigation. Okay, and then one more question. Like if we look at 0, 2, there are 5 points close to each other. 0, 2. Yeah, these points close to each other. Yeah, so it is a genuine ambiguity in what is considered an outlier. That's the thing. Like, are these things outliers or not? I mean, there's no single definition. So that's why I was saying earlier, this is very up to like human interpretation. And the people who made isolation forest and made the default hyperparameters of it had particular thoughts on that. But it might depend on what you consider an outlier for the work you're trying to do. Okay, let's keep going. Yeah, so what I really want to do is here. Okay. Yeah, we can look at the capital gain for these cases. That's right. So if I look at the capital gain for these predicted outliers, you can see it did seem to find the things with crazy high capital gain as outliers and these pretty high capital gain, but it also found a bunch of people with zero capital gain. So clearly it picked some people as outliers for reasons other than they had a massive capital gain, because a bunch of these people had a zero capital gain, which is very normal, but maybe something else about them was unusual. I was thinking outlier could be found when we have a Euclidean distance between the mean value and the large distance. Yeah, okay. I won't directly address that right now. I want to keep going to other data sets. So here's a movie review data set, if you remember that from lectures 4 and 5. So here are these movie reviews. I mean, it's hard to say what an outlier is for text. So the one thing I thought about is, well, we could at least look at the length of the reviews if we wanted to have some fun with this. And it seems like there's some pretty long review in here. So there's a 14,000 character movie review. And I mean, I just thought it'd be fun to print this out. Not really. Here it is. So I guess that would be your outlier when it came to movie reviews. It's I can't even process this. Okay. Anyway, that was more just for fun. It's a bit hard to say what outlier is in terms of text. The Amazon product ratings data. So that was a more recent one that we looked at. It's pretty hard to talk about outliers here because the ratings are just from 1 to 5. So you don't really have outliers in the rating. You could have outlier products, and we did talk about that in lecture 14. Like this item has way more reviews than anything else, or something like that. Yeah, the housing data. So you probably remember this housing data. from lectures 10 and 11. And so again, you can do the pandas profile thing. You could also do the isolation forest thing, which I didn't do, but I think it'd be kind of fun. Yeah, so again, you can look through and see if there's, so this looks pretty, again, just looking at one feature doesn't tell the whole story, but this makes me think, okay, there's some big lot areas. If the scale is going all the way to 200,000, I'm presuming it's square feet. So yeah, lot area might be something to look at. I don't really want to deal with that. But I would like to, I just think it would be fun, so I'll do that later. It'd be fun to see what it checks. Okay, so lot area looked like it was kind of interesting, so we can look at lot area a bit more, and we can maybe crank up the number of bins a little bit. So yeah, we see some very big properties here. And so those are potentially anomalous or outliers. We can also do a scatter plot of the lot area versus the sale price in the training data, and we can see those as well. So here's where it gets interesting. So there's kind of this trend of like bigger lot area gives you bigger price, but it's not, I mean, it's not like a perfect trend, but these ones are, you're not really you're getting diminishing returns for having a ginormous property. And so if you're doing something like linear regression and you're only looking at lot area, this would be problematic because these outliers would kind of potentially obscure the main trend here. Maybe the main trend is that there's kind of this steep increase of sale price versus lot area. But because of the outliers, your linear regression might do something like this because it's trying to do a good job of these cases and getting messed up. Questions? Okay. Okay, yeah, are these outliers a problem? So in reality, we don't have 200,000 because we're scaling things. And so we actually have scaled area, which looks more like this. And remember, the interpretation of standard scalar is that it's in terms of standard deviations from the mean. So what this is saying here is that this lot is 20 standard deviations above the mean, and this is about 16 standard deviations above the mean. So yeah, I mean, at least it's not like a million, but these are very, very, very big values compared to everything else we have, which is in like a couple standard deviations above the mean. So that could certainly affect our model. This is just a histogram looking at scaled values less than 5, and so that's like this left chunk of the histogram. So yeah, what's happening here is that most of the points, the houses are between or within one standard deviation of the mean lot area, but then we have these outliers for lot area. Okay, so what I'm looking inside of this standard scalar object, and it's saying that the average lot area is 10,000 and the standard deviation of the lot area is also around 10,000. But what we could do is we could subset it to just remove those giant lot areas. So we could say, let's throw away the lot areas above 100,000 square feet because that's just a very strange house that may mess things up. And then let's see what the mean and standard deviation are of the lot area. And what you can see is that the standard deviation is actually a lot smaller. So what's interesting is those couple of outliers are making the standard deviation of lot area really big, which is causing standard scalar to divide by a bigger number. And that's why everything's kind of squished here between -1 and 1, whereas normally when you look at standard scalar, it'd probably be more like between -3 and 3 for the bulk of the data, or -2 and 2. But the outliers changed our pre-processing, and probably not in a devastating way here, but it's something good to note. So let me actually okay. Oops. Okay, so let's also talk about min-max scalar. We hardly touched min-max scalar in this course, but if you remember way back when we talked about standard scalar, that was standardization. There was also normalization, which squished things to be in between 0 and 1. And so what we can do here is we can transform the lot area with the min-max scalar. And what we see is that min-max scalar puts things in between 0 and 1. And normally you could kind of expect values all over the place, but because there's this lot area of size 200,000, and min-max scalar has to put the smallest thing as 0 and the biggest thing as 1, the 200,000 became the 1, and since it scales proportionally, all the rest of the data is kind of squished in between 0 and 0.1. And so if your point of doing min-max scalar was to have all your features kind of smeared between 0 and 1, now this feature with the outlier is actually mostly living between 0 and 0.1, and that could affect the model and kind of bias how important it thinks the feature is. It could make it think the feature is less important because it's not varying that much most of the time between 0 and 0.1, but it's just because of this outlier. And so, yeah, what this is saying, well, yeah, it's saying 95% of the lot areas are less than 0.7 after scaling, and that could kind of mess up your modeling a little bit. Outliers are more important in linear regression than in random forest regression. Excellent question. Okay. I think it is fair to say yes to that question. But furthermore, outliers in the feature values in X are kind of a different story from outliers in the target value in Y. And we're going to talk about that distinction in a second. But actually, I think either way, linear regression gets hit harder than random forest. Random forest will not care too much about this. I have a demonstration later on in the lecture where I actually put in an outlier and then compare linear regression to random forest, and they do both get affected. So maybe I'll say generally yes for now, and I'll show you some more detail in a minute. Okay. Yeah, so there's this scikit-learn page that talks about different scalars on data and their effect on outliers. So this is a really good read. Maybe I should add this to the course webpage, but they compare. Anyways, we don't need to go into that right now. But a couple things they talk about in there is this robust scalar, which tries to ignore outliers. So basically, it's taking the giant value of 200,000 square feet and leaving it as a giant value of 50, so that the bulk of the data is between like -3 and 3, like you would normally get with standard scalar, instead of everything being compressed by the presence of that outlier. There's also quantile transformer, which is like a very extreme transformer. What that does is instead of scaling and looking at the values, it actually just looks at the order of your numbers. So it says, okay, the smallest lot area is going to be called 0. The next smallest is going to be called 0.01. The next smallest is going to be called 0.02. And that way you get this like uniform distribution. So after you apply the quantile transformer, it looks very uniform between 0 and 1. But that means you've completely thrown away the magnitude of the lot area, and you're just talking about basically the ranking of the lot area. The question is, why would you ever do that? I mean, it is in a sense like the most robust thing ever, because if you have a trillion square feet or whatever, it's not going to care. It's just going to keep everything like this. So I don't. Yeah. Oh, I have that right here. So I make one of the lot areas some absurd value, and then you see that the quantile transformer doesn't care. So I think it is probably less commonly used than all these other scalars, and I don't have like a slam dunk use case to tell you right now, except that it will completely ignore the size of the values, which might be a good thing, especially if you have big outliers. What does the number on the y-axis represent? These are counts, because this is a histogram, so it's saying I have 15 of them at value 0, 7 of them at value 0.1, etc. So where is it? Yeah, this is it. I'm histogramming. Okay, let's break and resume at 11:45. I didn't quite pause for questions before the break. Are there any questions about this stuff before we proceed? Can you explain the x-axis again? Sure. So what I'm doing is I'm transforming the lot area feature. So we had like standard scalar, min-max scalar, all these things that would transform our features into like kind of small numbers close to 0, that kind of thing. And then what I'm doing here is I'm making a histogram to just see what types of different values we have. So, I mean, the values themselves are just a whole bunch of numbers. It's hard to look at. So I'm making a histogram of them just so we can see, okay, most of them are around 0. So the x-axis is the transformed value of the lot area feature, and the y-axis is the frequency of values within the bin. So we have a small number around 50. We have lots around 0. Does that answer it? And quantile transformer. Well, so the plot is of the same thing. It is still the histogram of the transformed thing. So the x-axis is still the transformed value. So if I show you the values, you'll see they're all between 0 and 1. And when I make a histogram of it, not only are they all between 0 and 1, but there's kind of equally many between 0 and 0.1 as between 0.1 and 0.2 as between 0.2 and 0.3. Because that's how quantile transformer works. It kind of just takes them in order and then puts them in ordered values between 0 and 1. All good. Okay. Anyone else? Okay. Oh, I did do that. Okay. Mean versus medians. So the biggest values don't get thrown out. They get mapped to 1, but the value of the biggest values gets thrown out. Like if the biggest value is 8 times bigger than the second biggest value, that information gets lost, because if the biggest value is 25 times bigger than the second biggest, it would have looked the same after transformation. And so some information does get thrown out. Put another way, with standard scalar, you can invert what standard scalar does. It shifts and then scales. You can unscale by the standard deviation and shift it back, and you'll get the original data. With quantile transformer, it does kind of throw away some information in a way that, I mean, intuitively, that standard scalar doesn't, because you can take that biggest value and change it to whatever you want, and as long as it's the biggest value, it'll be transformed to 1. Okay. Means versus medians. So some of you may have seen this before, this idea that the median is a more robust statistic than the mean, but I want to briefly mention it for those who haven't seen this before. So here's a list of numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 9, 9, 9. And we can look at some summary statistics. So the average of this is 10,000. The median of this is 5. Oh, whoops. Okay, I was going to change it to 9999 later, but I had left. Yeah, okay, start again. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the mean is 5, the median is 5, the standard deviation is 2.5. I can also look at percentiles. I guess it's not necessarily the case that everyone in this course is familiar with percentiles. So what percentile 75 does, it says give me the number such that 75% of the values are less than this. So it basically says, put them in order and then get me the thing 3/4 of the way down the list. And this says, put them in order and give me the thing 25% of the way down the list. And the median is actually also known as the 50th percentile, because the median is put them in order and give me the thing 50% of the way down the list. So this is just another statistic that people will often look at. So yes, the point is what happens, I already kind of did the punchline, but what happens if I change this value to make it an outlier? So you have this big value in your data, and what happens is that some of the statistics are massively affected and some of them are not affected. So the mean gets pulled way up because it's simply adding up all these numbers and dividing by 9. And so if one of the numbers is huge, the sum of the numbers is huge, and so the mean is huge. But the median does not care about this. The median is saying, put them in order and give me the middle. The middle is 5 either way. Likewise, the standard deviation is the statistics that depends on the mean and depends on the variance, both of which are going to be affected by this big value. So the standard deviation went way up from 2.5 to 31,000. But this interquantile range, as it's called, stayed the same. And so what I would say is that I would say the median is a statistic that is robust to outliers. If you add a big value, it doesn't really change. It is a measure of kind of the where things are at that is robust, as opposed to the mean. And this interquantile range is a measure of spread, of how far apart things are, but it also ignores outliers, whereas standard deviation is also a measure of spread, but it is deeply affected by outliers. And so what does this all have to do with applied machine learning and what we've been doing? Well, the standard scaler, for example, computes the mean and divides by standard deviation. And so it's really affected by that. I don't remember exactly what the robust scaler does in scikit-learn. I can check. But if it did something like shift by the median and divide by this interquantile range, that would be a case where it would be robust to outliers. I don't know if that's exactly what it does. But the way you pre-process things, you might use some of these robust statistics and it might make outliers affect you less. Furthermore, okay, so we talked about quantile regression in the second lecture on regression, when we used quantile regression to get prediction intervals on our, so we used the light GBM, I believe, and we said, give me the 25th percent quantile and the 75th percent quantile, and we used that as a range of my predictions. So I think my predictions from 100,000 to 150,000. Quantile regression is another way to, let me write this all down. It's getting too messy. So I mentioned earlier that, actually, just one other second. Okay, I just mentioned earlier that thinking about outliers in the features and thinking about outliers in the targets, we kind of want to separate that in our brains. And this was a good opportunity to separate that. So we care about this mean median stuff in terms of pre-processing. And so outliers in X will come into play there, but we actually also care about this mean median stuff in terms of our regression. Now, with classification, you don't really have Y being a numeric value. I mean, if Y is fraud or not fraud, it's hard to have an outlier there. But for regression specifically, not classification, there's this extra type of outlier we need to think about, which is outlier in Y. And for that, we have our own whole set of things, which I'm going to talk about in a minute. Questions? Okay. So I'm going to load up this housing data again. And again, I'm just displaying bad habits and copy and pasting a bunch of code. Okay, so here's what I'm going to do. I'm going to take the encoded training set, which is this thing with standard scalar and one-hot encoding, all that stuff. And I'm going to do linear regression. And I'm going to look at the coefficient for lot area. And I see that it's 3,000. And we talked before about the scaling and how to interpret this with the units and all that kind of stuff. And the largest lot area, as we talked about before, is about 20 standard deviations above the mean. And that happens to be training example number 163. So how does our model predict on that property number 163 with the huge lot area? Well, in this case, it actually does okay. So the true value was 375,000, and I predicted 318,000. So far, it's not doing anything devastatingly bad, at least on our lot with the big lot area. Although I guess this is, I don't know, it has 20% error. Not amazing, but it's okay. Now I want to talk about splitting things up further. So there's two types of outliers you might encounter. There's an outlier in your training data. So you may have a giant value of a lot area or a giant value of a house price, and that's going to affect the trained model in fit. And if the outlier was a mistake, that's going to mess up your model. The other type of outlier for you to be on guard for is the outlier in test data or deployment data. I think I would really rather say deployment here. So here's the thing. You may have, your data set may be messed up, and that may mess up your model, and you absolutely need to care about that. But even if your training set is perfect, you may want to ask yourself, what if during deployment, I get a feature value that's super out there? What if I need to deploy on a lot area of 50 acres in an urban environment? What's going to happen there? And so that's just like another thing to be going on in the backs of our minds. And in that case, that couldn't be an outlier in the Y because we don't have the Y values in deployment, but it's more about an outlier in the X and something else to keep an eye out for. Okay, but we're going to talk mostly about this. I don't know why, to be honest. Felt a bit randomly placed here, but I can't remember why I put it there. Okay, so let's make a bigger outlier in lot area this time. So our real outlier in the real data set was 20 standard deviations above the mean. Let's make xtrain corrupted, where we ourselves make a copy of the training data and then change the lot area to 10,000 for the 0th example to 10,000 standard deviations above the mean. So it's like the size of the whole Vancouver or something is this lot area. And what I'm going to do now is I'm going to fit a linear regression on this corrupted version of the data set. And we're going to look at the coefficients. So these were the coefficients we had before. We had a coefficient of 3,000 for lot area. And what we have now is a coefficient of 2 for lot area. So here's what's happening here. And notice all the other coefficients change too, which is normal. So here's the explanation for this. Remember how linear regression makes predictions. It multiplies the coefficient by the feature value. If you had a reasonable sized coefficient here, like 3,000, and then you multiplied that by 10,000 standard deviations above the mean, it would get you such a big value. Your prediction would be like $1 trillion, and that would give you such a big error. It does not want to do that. So it prefers to basically ignore the lot area feature, not completely ignore. Coefficient of 0 means completely ignore, like it's multiplying the value by 0, but to downplay this feature a lot and make it very unimportant, give it a small coefficient, just because of that one outlier. And so you can see having outliers does really affect the trained model. Just having that one mistake in lot area of having such a big lot basically forced our linear regression to almost ignore lot area. And it's not going to be as good of a model anymore because lot area is actually presumably useful for making predictions, but it has to do a small coefficient just to accommodate that one training example. Questions about this? So my take-home message here is if this happened by accident in your data set, it will actually mess up your model. Any questions? And you know what would have been really great here? That might be too late. It's too late. I would have loved to give you the test error on both. Okay, even though I'm sorry if I'm trying to drive everyone crazy by this, but I would really love to compute the old test error is 86, and I was I see. So the test error only went down a little bit. That is interesting. So what happened here was, I guess having the lot area be taken into account was nice, but if you kind of more or less ignored it, it didn't kill your model that bad. Probably because there's some other features in here that are correlated with lot area, and if you have to disregard lot area, you can kind of use another feature to give you that same information. That would be my hypothesis here. But let me add another to do. Don't call both of them LR so that you can actually compare their test errors next to each other. I just shouldn't have named them both the exact same variable name because that messed everything up. Okay. Question, what should we do if we have outliers in the training set, but we know that these exist in deployment / the real world? Yeah. I guess one answer to that would be like go with a simpler model. So for example, for ridge, the complexity hyperparameter is alpha. And the bigger you make alpha, the smaller it'll make coefficients. And so if you're worried that you might get some erratic values in the features in deployment, you could crank up alpha, which will lower your scores a little bit, but it will also lower your coefficients a little bit, which will mean that it'll be making less extreme predictions and not take a particular feature into account too much. And for any type of model you're using, I guess my kind of gut feeling is if you make it a bit simpler and overfit less, even if that gives you a worse cross-validation score, I would feel a bit safer with how that model was going to treat weird deployment data. The other thing you could do is you could have in your deployment pipeline some sort of outlier detection and try to say, hey, this looks a little messed up. Maybe I'm going to treat this as a missing value and just impute it because I can't be that I have a lot area of 10 million. And then you could actually add that into your pipeline of deployment. Okay, let's keep going. What happens if we make a bigger outlier in the targets? Okay, right. So this is, again, I want to hammer home. Outliers in X in your features versus outliers in Y in your targets are not exactly the same. And it's not a coincidence I'm using the housing data set. I needed a regression problem here so I could make an outlier in the targets, which wouldn't really work in classification. So what I'm doing here is I'm making a Y train corrupted where the first house is now worth $1 billion instead of, what did it used to be? Hey, that's not nice. Okay, so it was actually $157,000, but I'm corrupting it and saying it's worth $1 billion so you can see what happens to my ridge model. And so what happens is it got kind of severely compromised. So it learned these massive coefficients in all the different features. It was trying to like twist itself in a weird way to somehow predict a huge value for this, just this one training example, and predict normal values for all the other houses. And so it gave itself these massive coefficients for all the features such that they all lined up perfectly with their positives and negatives just for training example number 1 to give you a big prediction. And it's basically garbage, right? So this just single training example out of 1,000 totally tanked our linear regression. And when we make predictions, they don't even make any sense. It's saying this house is worth negative 150,000 when it was actually worth 300,000. Everything just got totally messed up. So in this case, I am confident in saying, unlike last time, I'm very confident in saying the test score is going to be horrible here. Oh, because we just have, yeah, okay, this, we have an R-squared score of negative 7,000. It's just complete garbage. So that single mistake in our Y, setting that one house to $1 billion, completely tanked our linear regression. And so it makes crazy predictions on all the training examples. Yeah, I don't even really need to say that. So here's the real house prices, the Y train histogram, and here's the predictions. So it's just garbage. It's predicting, this is 10 to the 7 here. So what is that? So it's going like negative $10 million to positive $60 million in the predictions. It's all just trying to accommodate that one corrupted example. And we go into much, much more detail on that in 340. Interesting question in the chat. Can we normalize the target value? So that's actually the exact next thing I was talking about. So if we happen to have log transformed our targets, we will be a little safer. Just because $1 billion is not as extreme and crazy in log space. It's just 9, like or 10 to the 9. So yeah, when you do things in log space, you can actually survive that a little better. And get reasonable predictions, and your test score will not be as horrible. So that's good. So yeah, log transforming helps with that a little bit. And it's basically the interpretation of log transforming, if you remember, is like one extra bedroom gives you like a 10% extra boost. And so you can get up to that $1 billion by just like doubling the price a bunch of times. And so yeah, it does help. Okay, so now as promised earlier, we'll talk about random forests as well. So how does a random forest deal with Y train corrupted, where the first house is worth $1 billion? So in this case, whoa, my gosh, did not mean to press whatever hotkey that was. Yeah, so on some, I don't remember what end is, so I don't feel like using it anymore. It's getting some reasonable predictions here. So the thing about random forests is the following. Think about decision trees from a long time ago. It's like partitioning and partitioning, if this, if that, if this, if that. And then at the bottom, it's like, okay, I have this left. And so I'm going to predict. If you meet all of those criteria all the way down the tree, here's what my prediction is going to be. Because we only corrupted one house, the first house, and set it to $1 billion, only that path down the tree is going to have a ridiculous prediction at the bottom. And so when you're done and when you use this on test and deployment data, it's only going to give you the silly values if you follow the same path down the tree as the crazy one. And so for other houses like this one I picked, house number 800, it's still giving you normal predictions. It doesn't care about that 1 billion because that's like a different path down the tree. Now, random forests are actually a bunch of decision trees, but that intuition more or less holds. So if I go back to predict on the messed up point itself, which is house number 0, then I get a big prediction of 650 million, which is kind of close to the billion. So if I have another house that was similar to the one that got messed up, I will also get crazy predictions. And so here I have a histogram of all the predictions again. And basically most of them are like fine, and that like a couple of them are super massive. I don't know. I don't actually love these histograms that much. I don't know about you. This is pretty misleading. Okay, let me, here's what I want to do instead. I don't like these that much. Oh, that's really what I wanted to show you. It's only predicting above $1 million for 4 houses, and for the other 1,000 houses, it's predicting less than $1 million. So basically, there seems to be 4 houses that are similar enough to the crazy one that they went into crazy land as well. Because I don't think any of the houses were actually worth $1 million. Yeah. So there was no house worth over $1 million in the training set, but only 4 of them went into crazy land here. And yeah, it said 10, and again, I believe it's because of the random state. I'm sorry about that. It's annoying to not get the same results when you run the code again. Oh, now only one of them went to crazy land. Well, that's not really the message I want to be sending to the future of applied machine learners. Oh, come on. Okay, last time. Don't mess with me, please. Thank you. Okay. Sorry about that. Okay, I was just changing the random state. Okay, yeah, so about, in this case, with this random state, 5 of the predictions go into crazy land. And if I go back to the original uncorrupted case, then I don't get any predictions in crazy land. None of them are bigger than 1 million. So to answer the person's question from an hour ago, random forests are safer here because linear regression is like a global fit. It's like a single line, not a line, a single regression surface that is supposed to do well on all the points. And it is trying to optimize for something that involves all the points. And if you mess up one point, it messes everything up. It tries to like change all the coefficients to accommodate the one point in crazy land, and everything gets messed up. Random forest, it's kind of like those bulkheads on a boat that like prevent the water from spilling. It's more compartmentalized. The things that go down the tree together with the weird training example, those ones are going to be weird, but the rest of the paths down the tree are completely unaffected because it's not this global fit. It's like each thing is done separately as it takes its path down the tree. Questions? This is, I like this stuff. I don't know about anyone else, but I think this is fun. Okay, the last thing I want to talk about is robust linear regression. So yeah, linear regression seems to be easily derailed by even a single training example with a completely messed up target value. And there are ways around this. So for example, in scikit-learn, there's something called Huber regressor, which you can think about, if you would like, as basically ridge, but not getting messed up by outliers. And in fact, when you're done calling fit, it even tells you, hey, I think these ones were the outliers, and I kind of didn't let them influence me too much. So that's actually pretty awesome. And I've been debating myself, like in this course, I tell you, never use linear regression, always use ridge. And I ask myself, should I tell you never even use ridge, also use Huber regressor? And I don't want to be too opinionated and non-standard. So I'm not going to go that far, but I think it's fine. If you want to just always use Huber regressor, you'll probably be fine. It's just a bit less standard than ridge. And so I guess what I'm telling you in the course is use ridge as your default for linear regression, but have outliers always on your mind and always be looking for them. And keep in mind this Huber regressor tool, if you need it, that's basically like ridge, but robust outliers, but just has some extra messes that makes me hesitate to tell you always use this. Random idea, can we add a linear model at the end of the compartment set up by the random forest? Yes, you can. And I really wish that was implemented in scikit-learn. It's a very good idea that I believe works well in practice a lot. And I know a lot of people have had success with it, and I wish it was in scikit-learn. I wouldn't even be surprised if there's an issue or a pull request in scikit-learn where people are trying to get this in, but it's not in there yet. But yes, it's definitely a good idea. And if they put it in there, then I would teach it in this course for sure. But as it stands, random forest regressor doesn't have a linear regression at the leaves. It just predicts a constant function at the leaves. How are feature importances in Huber? So Huber has the coef just like ridge has coef. So it's all exactly the same. Yeah, this is a typo in their documentation. It should say coefficients. Coef is exactly the same, so you have that all carrying over to Huber regressor. So what I want to show you is I'm just going to run the code. I'm going to fit on ytrain corrupted. You'll notice you have this max iter like you do for logistic regression. That's okay. So I'm going to pass in the crazy $1 billion house, and you can see that I have non-crazy coefficients, which is awesome, or at least relatively non-crazy. And the predictions, I don't know why I'm predicting on that example, but anyway, I guess I could have left it. You're getting non-crazy predictions. That's what I'm trying to show you. So I can also do, and you do find the test data. So the Huber basically doesn't get super messed up, and outliers underscore. So hr.outliers underscore. It tells you which ones it thought were the outliers, and that doesn't look right to me at all. So it seems to have found a lot of outliers, but we know there's only one outlier, and so there's actually a hyperparameter epsilon, which kind of determines, yeah, the smaller the epsilon, the more robust it is to outliers. Getting a bit running out of time here. Seems like outliers can potentially be security threats to models, such as ones using self-driving cars. Really interesting point. Yeah, there's a lot of security threats to models, not just outliers, but that's a great point. I had some stuff about that used to be in the computer vision lecture, but I moved it to the ethics lecture to make room for the stuff on multi-class classification. Long story short, I will be talking about that kind of stuff. Like AI safety is kind of the term there. I will be talking a little bit about that. And here I thought scikit-learn was perfect. What are the examples of libraries that have that function? Yeah, I could give you a whole list of complaints about scikit-learn and my wish list. It is definitely not perfect. It is made by humans, probably many of which are volunteering their time. At least I know one person who is. What are examples of libraries that have that function? I don't know actually, but you might be able to Google it. Can we hear a bit about your complaints? Yeah, like, so for example, with random forests and decision trees, you shouldn't have to one-hot encode categorical features. For like linear regression and stuff, it makes sense that you have to one-hot encode categorical features because that's like the math of linear regression kind of requires it. Like you're multiplying stuff and you can't multiply a coefficient by, by a string. But for random forests, like with the splitting, it would be nicer if it could directly take in the categorical variables because there's no theoretical reason And there's actually something called cat boost that I'll probably talk about later that is like I did mention cat boost to you, that like more natively handles categorical variables, which might be a little better. Anyway, there's a few other things, but scikit-learn's pretty great overall, and I'm very appreciative to the people who made it. 2 minutes left, so I'll just quickly say outliers are not always bad. I did already talk about this a bit. They might be just regular data that are crazy values, and maybe you want to leave them in. So you have to think pretty critically about, why am I looking for outliers? What do I want to do about them? Do I want to throw them away? Do I want to use a Huber thing? Do I want to change my pre-processing? There's lots to think about pretty much with any data set, which is why I feel like I should move this to the first half of the course, because it's more of a fundamentals lecture than a here's a common special case lecture. And there's the different types of outliers. Sounds like a huge mess. Yeah, I guess so. Yeah, my take home for you here is I want you to have this on your mind all the time. I want you to have in your mind the distinction between outliers in X, outliers in Y, outliers in train, outliers in deploy. And even just having this on your radar will make me very happy, compared to you all going out into the world not thinking about this whatsoever. So that's that. Yeah, here is the summary. I won't read it out to you because we're out of time. So I will end here, and I will see you back on Tuesday, and we'll talk about time series data, which should be a lot of fun. See you then.